Good afternoon.
Good afternoon.
All right, so last class we were finishing off on 7.36. So this one is a long cylindrical heating element of diameter 12 millimeters. Thermal conductivity was given, density, and specific heat of that heating element. Is installed in a duct for which air moves in cross flow over the heater at a temperature and velocity of 30 degrees Celsius and 8 meters per second, respectively. Part A, neglecting radiation, estimate the steady state surface temperature when per unit length of the heater electrical energy is being dissipated at a rate of 1,000 watts per meter. And then part B is if the heater is activated from an initial temperature of 30 degrees Celsius, estimate the time required for the surface temperature to come within 10 degrees Celsius of its steady state temperature. All right. So now we are looking at our givens. We have our long cylindrical heating element, diameter. We have properties of that heating element. Okay, and then we have a velocity, T infinity, cross flow, and they ask for the surface temperature for steady state with that power, right? They say neglect radiation, so we'll put that over here too. All right, so with part A, we started doing that. We said COE, we have energy out, we have energy generated, and it's steady state, as was said. So we have convection and the electric power coming in. So we set up here, and we have the Newton's law of cooling. So we have our we have to get our average convection coefficient, and we have to ultimately get the surface temperature. Okay, so where do we want to start to get this average convection coefficient? What's our first step here to get this parameter here? What's those, we talked about it last class, but what's the kind of three major things that we have to determine when we're really looking for a convection coefficient, or equations to get the convection coefficient?
Nusselt.
The Nusselt number, okay? So that's ultimately what we want to get, right? So ultimately we want to get the Nusselt number. Right, and we can write out what that is. So we're looking for the average. Okay, so there's the general one right here, okay? And if we look at that one, we have diameter, we don't have the fluid thermal conductivity, and we're looking for that convection coefficient, and we don't have the Nusselt number, right? So if we want to go grab well, I'll start with this one. The thermal conductivity of the fluid, okay, what temperature do I use?
The average.
Yeah, the average. So that'll be the film temperature, which is T surface plus T infinity over 2. The challenge is we don't have T surface, right? Because we're solving that. So we have to assume one or guess, right? So I'm going to guess 450, okay? nice even number. We have T infinity, which is above, right, 30 plus 273. So, we have 303 on T infinity. We know the surface is going to be much hotter because we have heat coming from electric heater. So then the average will be something above, right? So pick a nice round number. We got to assume right here. We can always check it later on. And really, when we're using this average temperature, we're using it for properties. So really, we want to check how much the properties are changing with the temperature later on. So even if this was 500 and we assumed 400, the properties might not be changing that much over 50 Kelvin. Okay. All right. So if we get that, we get 0.0373. One common mistake I would see here is using the thermal conductivity that was given in the problem, which is for the heating element, not for the fluid. Okay, and the fluid's 0.0373, and the heating element's 240. So you would have 4 orders of magnitude of an error by doing that. Okay, so that's a huge kind of mistake there. All right, so now we have that. So we're ultimately trying to get the convection coefficient. So we need to get our Nusselt number that was set. So how do we determine which Nusselt number or Nusselt number equation to get? What are our main things we're looking for to go into the book and search for the relationship to use? If you're going to hunt this down in the book, within the chapter, what are the main factors you're looking at in this problem to get the right Nusselt number equation?
Geometry.
So geometry. So we have cross flow cylinder, right? Anything else? What else?
The Reynolds number.
Yeah, so laminar turbulent, right? So we would go for Reynolds number, right? So we got to do that, yeah. And then one more thing.
The Prandtl number.
Yeah, well, that's properties, but that'll be a lookup. But the main, like, to find the right equation, like within the equation, we're gonna have to use a Prandtl number, yes. But one of the things that has to decide what equation to use, okay, or figure or anything like that. The last one, I'm not sure if anyone, is the local versus average, right? And we want the average because we have the bar over our convection coefficient. We're looking for overall over the cylinder. We're not looking for a single point like right here on the cylinder or here, because the convection coefficient changes as it goes around. The flow goes around the cylinder. We're looking for overall in the cylinder, not at a single point right there. If we were interested at a single point, that's where we got to figure out how we get the local value. Okay. So we have average. So those 3 things should help us, right? So we have to get our Reynolds number. We have diameter, velocity. We need to get our kinematic viscosity. And again, let's make that a little better. At the temperature of the film. we get 32.39 times 10 to the negative 6 meters squared per second. All right, so then we have that. Our Reynolds number is 2964. And we have, then, is that laminar or turbulent?
Would it be laminar?
Yeah. Okay, so we have laminar. All right, so now we have these main things to go hunt down our equation. Okay, so we go and look for these things, and we see a Nusselt number equation that'll work for us. There's actually 3 of them for cross flow over the cylinder, but we're going to use the one that's all pure equation. The 2 others require table lookups of different properties dependent, or different coefficients dependent upon the Reynolds number, which you could use too and just cite that. This one, although lengthy in equation, works for laminar or turbulent in this case. All right, so we write this giant equation down. And we're finally done writing it. This is equation 7.54. And as we said in chapter 6, the Nusselt number is a function of Reynolds number and Prandtl number, and that's what we see here, right? We have our Reynolds number calculated. We just need to go, so we have Reynolds number, we just need to get our Prandtl number. We go and get it, and we get 0.686. All right. So then we put this equation in our calculator. We ask a friend to put it in their calculator. We get 2 different answers, and then we pick our favorite, and it ends up being the right one, which is Nusselt number of 27.6. Okay. Okay, so then if we work our way back, we have now Nusselt number, so we can get our convection coefficient, right? Oh, that's not our answer. We got to take it one more step. Go back up, and now we have convection coefficient, so only the surface temperature is unknown. So we get 612 Kelvin. And then we can check our film temperature, whether our gas is good, and really just check the properties, how much they change with the new film temperature. And you would iterate again if they change a lot, right? Or on a test, just say something like iterate again if, to check, due to different property values or a bad guess on my average on my film temperature. Questions?
Say if we were to do that on a test, like, hypothetically, how would you grade that? Would like that be sufficient, or would you have wanted us to like actually iterate it again?
You just tell me your process, like tell me iterate, just do this, take the new T-film and iterate again, or you could just say that, or go through with the grabbing new properties, calculate your surface temperature again.
Okay.
As long as you know the process, that's really my main grading point on exams.
Gotcha.
I had one question for the Prandtl number. Can we use the equation, or do we have to use the tables?
They both should come out with the same thing.
Okay.
Yeah, they're just conveniently putting it in the tables for you so you don't have to get the two properties, because it's a ratio of two properties, right? All right, so then part B. It asks to estimate the time, delta T, if the T initial, so it's initially the heating element is at 30 degrees Celsius, and then all of a sudden the heater comes on, we have convection on it, and it wants to know how long it takes to get to temperature, within 10 degrees of the steady state temperature. So where do we begin with that? What's our first step here? Is this a steady state problem? Part B? Or is it a transient problem? Transient, okay. So it's transient, yes. Okay, so we have a transient problem, right? So if we looked at, I'm just gonna do this. We already recognize it's transient, but I'm gonna do it anyway. We have COE, right? If we did that from the beginning, we have to leave the stored term in because it's transient, right? En now is still canceled, right? So we're going same thing here, but we have the stored term. All right, we have still convection. Oh, skipped the whole term there, huh? per unit length, so that's why I don't have L in here. Make that a little cleaner. All right, so if I start and I have this step right now, right, and again, I don't have L here or here because it's per unit length, right, E prime. All right, so I started this step. What is this start looking like? Is this an analysis in this first step that you've seen before? We said transient, right? So we left this term in on the right. What have we done that has transient analysis? So chapter 7 is just getting the convection coefficient. So the analysis we've done before. What analysis have we done that deals with transient?
Transient conduction.
So what was that?
Transient conduction.
So transient conduction. So what was our main analysis that we did? So that's chapter 5, right?
Was it lump capacitance?
Yep. So lumped capacitance. All right. So we have transient. So transient, you first want to see if you can do lumped capacitance because it's the easiest transient analysis to do. And if you can't, then you start going into the more complex ones to get a correct answer. All right. So lumped capacitance, which means everyone's favorite, we need to do our Biot number, right? All right, so then Biot number, we have convection coefficient from the last part A. We can get our radius, and then this is the solid, right? This is the actual heating element's thermal conductivity. So we have that was given in the problem. We do this, and we get, which is much, much less than 1, so we're good there. So we can do lump capacitance. Okay, so lump capacitance is where we're just assuming this temperature right here is the same temperature throughout, right? That means this can be related to this, right? Being the same temperature. Okay. All right. So we have lump capacitance, we have convection, we have electric. So we basically we have convection right here, right? We have energy generated, which is our electric power. So we basically just go to chapter 5 because we've already in chapter 5 integrated the different forms to solve lump capacitance, and we find the version that shows us that has convection and an energy generated. Okay, and that is this one.
Is that negative EX?
Negative, right? Which one? Where? Which one are you asking
Is
about?
is the E negative?
Is the the E? No.
Okay.
It's just my terrible writing, or my fast writing, I should say. so this is our equation 5.25, where A is defined as HA over rho VC, and B, heat flux area, energy generated, divided by density, volume, specific heat. Okay. So I'm not going to spend tons of time on this part because we did chapter 5 before. We do not have any surface heat flux, right? We have convection, right? We have electric power, okay? So, but there's no applied surface heat flux, like an external heat flux, like a heat lamp or anything like that. Okay, density, volume, area, specific heat. We have all those from geometry and the properties. So we can now solve for temperature, right? We just need to figure out, or for time, sorry. We need to figure out temperatures, right? We have T infinity, initial temperature was given of 30. What temperature do we put in there?
Within 10 degrees of the 612.
Yeah, so in this case, it would be heating up, right? So we would have temperature of 602 Kelvin, right? Because when it reaches steady state, it'll be 612, right? It's starting off at 30, okay? So, yep. So then if we put that in, we will get time of $290 seconds. Okay. Questions? Okay. All right, so then